So now we're ready to describe the very famous PageRank algorithm behind Google and one of the reasons for Google's success on the technical side. It says that given this matrix G, which is H, okay, plus 1 over n times W vector times outer product with one vector, the whole thing theta percent of the time plus 1 minus theta, the other percentage of the time, is multiplying by this randomization vector, okay, giving you an outer product of matrix all ones. Okay, you define G as such, and then you're going to iterate. Pi transpose at time k plus 1 is simply the last iterations pi transpose, all these are vectors at iteration k, okay, multiplied on the right, not by the H matrix anymore, we got to modification we needed, by matrix G, and let k keeps on going, and you are now actually guaranteed to converge from any initialization pi vector to the equilibrium transpose equals pi star transpose times G matrix. In other words, the importance score is actually the dominant left eigenvector of matrix G, not just H. We're skipping the proofs in linear algebra, but the end result says that with these two modifications we can guarantee a convergence to a uniquely defined left eigenvector with eigenvalue 1 relative to this matrix G. And this can be either computed if G is small enough directly or iteratively through this procedure, iterating over index, iterations indexed by k. Now, if you still want to take the two more remaining steps, then you'll be done. One is you want to normalize. Remember, so far we haven't normalized this pi vector yet. Okay, if you really want to know the relative scale, you want to normalize them. So the new pi I is really the original pi I divided by the sum of all the pi's entries. But the most important thing is actually ranking now. Remember, we started with ranking, not computing scores. Computing score is a means to the ends of ranking. And ranking says, then you can look at either the normalized or the not normalized version of pi, and then whichever node has the highest pi is ranked the highest, then the second, then the third, and keep on going. And the top 10 will be going on to the first page of the search results. And you can see that if ranking is what you care about, actually you don't exactly see the relative scale. For example, this might be way more important than 2, which is only slightly more important than 3 by this computation of importance scores pi, but you wouldn't know. Okay, Google doesn't visualize that scale, and perhaps that's a good idea because that scaling may not be that robust, and hopefully the ranking itself is more robust. So in summary, we have constructed 3 matrices from H to H hat to the whole Google matrix G, and this iteration plus maybe normalization, and finally our ranking is how, roughly speaking, Google displays the ranks of the web pages